Hey, this video is for Math 112 Trigonometry, and this will cover section 1.3 involving solving triangles. So I will begin in the exercises on page 27, and I'll just go through the even-numbered exercises on pages 27 and 28. So we start with problem 2. We've got a right triangle here with legs of length 10 and 12. So, if we want to find the hypotenuse, we can use the Pythagorean theorem. And so we would say 10 squared plus 12 squared equals c squared. So that's 100 plus 144, or 244. And then we want to square root this. I mean, we could call it square root 244, or we could simplify the radical and do all of that good stuff. But the instructions ask you to round the side lengths to the nearest hundredth and angle measures to the nearest tenth of a degree. So we'll say c is the square root of 244. And so to the nearest hundredth, that'll be 15.62. Okay, so now we've got all three sides. So next, we want to find the angles. So we know that this angle is 90 degrees. It's just a matter of finding those two angles. Let's see here. So what we want to do, I would stay away from using this value in finding those angles, okay? I talk about this a little bit in the section. In the examples, I talk about using the most accurate values that you have to find other values, okay? Because this 15.62 is an approximation, and it's okay, it can affect your accuracy if you use it. Let's see. I guess I'll call this angle alpha and this angle beta. And so we could say that the tangent of alpha is going to be 10 over 12, right? The opposite over the adjacent. So that means that alpha will be the inverse tangent. I think in the sciences, they often use the notation arctan, which mathematics has kind of gotten away from. But in any sense, in any case, what we're getting at here is we want to find the angle whose tangent is 10 over 12, or 5 over 6, however you want to think about it. And we want to do this in degrees for these problems. So let's see here. So first of all, in the mode section, let me show you the calculator here as I'm working on this. Okay, so there's the calculator. Let's see here. Wow, this is really challenging. There we go. Okay, so there's the calculator. The mode key is right here. And then you can see, what is it, the third one down, or 1, 2, 3, fourth one down, radian versus degree. My calculator was in radians. I'm going to put it into degrees. And then let's see, there's the tangent button right there. So if I do second tangent, you can see that's the inverse tangent, second tangent, and then I'll type in 10 divided by 12, there it is, and then we'll hit enter. And so there's our answer, 39.8 degrees. Okay, so approximately 39.8 degrees. So that's alpha. And then beta will be 90 minus 39.8. You could also do inverse tangent 12 over 10. should give you the same answer. So let's see here. What is this going to be? 50.2. 90 minus 39.8 equals 50.2. Okay, so there's beta, there's alpha. We've got a right angle, and we've got all three sides, so our triangle is solved. And also, again, we can do inverse tangent, 12 over 10, and that'll give us a 50.194, which rounds off to 50.2. All right, so let's see here. That's problem 2. All right, problem 4. We've got our triangle, and this angle down here is 16.7 degrees. We've got a right angle there. I'll call that one theta. And our hypotenuse is 20, and we don't know the other two sides. Okay, so let's see, what can we do? Well, we can find theta right away. Theta is going to be 90 minus 16.7 degrees. And so that's going to give us, what, 73.3 it looks like? All right, because that'll be 10, 10, 9. There we go. Okay, so theta is 73.3. This angle is 16.7. This angle is 90. We've got all the angles. All right, now for the sides, let's see, that looks too much like a 6 there. That is actually a B. So for our sides, we could say the sine of 16.7 degrees is B over 20. And then we could multiply on both sides by 20 and say B is going to be 20 times the sine of 16.7 degrees. And again, it's really important when you're working with trigonometry, whether you're working with degrees or radians, is just double check that the calculator you're working on is set to the correct angle measurement. I actually was just doing a problem the other day and wasn't using this calculator. I went on to Google to use their calculator because that's what was available, and I didn't check to see whether or not they were in radians or degrees, and so that caused me to get a wrong answer. All right, so let's see here. We are in degrees, so 20 times the sine of 16.7, and that comes out to about 5.75. We're going to round this to the nearest hundredth. 5.75 for that one. Well, let's see. I'll do this two different ways, kind of something similar to what I do in the examples. I'm going to use the cosine of 16.7 and say that's going to be A over 20. And so now A will be 20 times the cosine of 16.7 degrees. And I'll see how close it is to what we would get if we used the Pythagorean theorem here. 20 cosine 16.7 degrees, and so that's going to be to the nearest hundredth, 19.2. And that actually comes out to 156, 19.156. And so, let's see what we get. If I take this 5.75 plus A squared equals 20 squared, and see what we get there. Okay, so 5.75 squared, 33.0625, A squared equals 400. So 400 minus that, A squared is 366, 9375. And so if we square root that, it comes out actually very, very close to what we had calculated a few minutes ago, 19.2. And that's fine. So here, you actually don't lose a whole lot of accuracy. You can see this is 155 and this is 156. And actually, I truncated that rather than rounding it. It's 1556. This is 1564. And this one is 1556. Yeah. So you can see they're off by a little bit, but nothing too bad. Okay. All right. So now we've got all three sides. We've got all three angles. So we're all set with problem 4. Okay. What else here? Oh, let's see. Oh, let's skip over to problem 8. In problem 8, again, we don't have any angles. We've got the right angle, and then 2 of the sides. So if I call this x, then we can say x squared plus 6 squared equals 12 squared. 36 is 144. Move this to the other side. X squared equals, oh, what is this? 108. Okay. So square root 108 to the nearest hundredth. 10.39. Okay. All right, so now we've got all three sides, and now we need to find the angles, alpha and beta. Okay. So we could say that the sine of alpha is going to be 6 over 12, which is 1/2. Now, if you know this already, like I said, I had to memorize a bunch of this stuff. This says that alpha should come out to be 30 degrees. So if we do the inverse sine of 1/2, or 0.5, yeah, we should get exactly 30 degrees. And that'll be 30 degrees, which means that beta is going to be 90 minus 30, which is 60 degrees. So there's our 3 angles and 1, 2, 3 sides. So we're all set with problem 8. All right, got 2 more here to look at. And all of this, you know, if you take a look ahead in the textbook, all of this is building up to word problems. Okay, where we use all these ideas about angles and sines and cosines and inverse sines and all this other stuff to solve problems. Trigonometry is really one of the most applicable mathematical disciplines. It gets used extensively in building and in surveying. I talked a little bit in the first video about astronomy. What was I going to say? Oh yeah, in building, what do they call it? It's not construction engineering. I forget what they call it now. But in engineering, one of the most, in terms of construction, one of the most important set of ideas goes back to the Greeks. Archimedes, I think, published or wrote about what's called statics, and that is, those are objects that are not in motion, and the way the forces operate on these objects. Something that's hanging, how much do you have to support it? Structural engineering, that's what I was looking for. And the concept of statics is very important, and how things are supported and how they're situated is very much a function of trigonometry and angles and lengths. Together with, what do they call that? Braking coefficients of some kind, the structural integrity of the materials you're using to build something also come into play as well. Okay, most of our word problems and applications will be fairly straightforward and will typically involve just working with triangles. If you're interested in engineering and statics, then those are courses that you take at higher levels. And I'm talking about them because I happen to find them very interesting. All right, let's see here. Problem 10. We've got a triangle where we've got one side of 3, an angle of 37 degrees, and that's all we know. Well, if this one's 37, then this one down here, if I call it theta, is going to be just 90 minus 37, and so that should be 53 degrees. Okay, and since those are both exact values, it doesn't matter, we can use either one. So I'll say the sine of 53 degrees is going to be equal to 3 over c. If I call the hypotenuse c and I call this one a. There's nothing so terrible about this. I could set it up to make the algebra easier. I'll talk about that in a minute. But what I'm going to do here is multiply on both sides by c and then divide on both sides by the sine of 53 degrees. So those cancel, and here c is going to be 3 divided by the sine of 53 degrees. So let's see what that comes out to. 3 divided by the sine of 53 degrees comes out to about 3.76. 3.76 for the hypotenuse. Okay, and then let's see here. I'll say sine of 37 degrees is going to be a over 3. Multiply on both sides by 3. And so a is 3 times the sine of 37 degrees, or about 1.81 for side A. Side C, 3.76. And this one over here, which I guess we can call side B, is just plain over 3, 1.81. Now, something I want to point out before I finish up with problem 12 here, and this will continue throughout the course, is that the longest side in a triangle is always opposite the largest angle, right? So in the right triangle, the largest angle is the right angle, and so the longest side is always the hypotenuse. Now notice in these two angles, this one's 53, this one's 37. You know, if our picture was drawn to scale, you know, it might look more like this. You know, this would be a little bit smaller and this one would be a little bit bigger. And then you would see that this is 3 and this is 1.81. This picture is, you can see actually this line looks longer than this one, even though this is 3 and this is 1.81. And that's very common when you're doing problems that have been drawn by somebody else. Is frequently you'll see something underneath it that says figure not to scale, okay? Which means don't trust the lengths that you see in the picture. Use the numbers to calculate the values. Okay, so you can see this side, 1.81, is opposite the smallest angle. This side is bigger than that because it's opposite the 53-degree angle. And then the largest side is opposite the biggest angle. And that's typically the way these things work. All right, so let's look at problem 12. And then that'll do it for this section. And then, like I said, I believe the next couple of sections have to do with word problems. And so we'll tackle those next week. All right, problem 12. We've got a triangle here. This is 58 degrees. That's 90 degrees. So that means this one is going to be, what, 32 degrees, right? We call that theta. Theta is 90 minus 58, which is going to give us that 32 degrees. And then we've got one side length right here, which is square root 7. Okay. Let's see here. So we need these two sides, A and B. Let's see, I'll say sine of 32 is B over root 7. And sine, let's do cosine. We'll do cosine. It doesn't matter. I could say sine of 58 is A over 7. Or I could say cosine of 32 is A over root 7. And so here B is going to be root 7 times the sine of 32 degrees. It's important when you do this in the calculator to make sure you come out of the square root before you put the sine 32 in there. Same thing here. I'll show you on the screen what I'm talking about when I calculate these. So let's show you if I can get the camera to focus on the calculator here. There we go. Okay, so we want to do square root 7. So there's the square root right there. So square root 7, right, like that. See, now if I hit sine, it's going to stay under the square root. That's not what I want to do. Okay, so what I want to do is I want to use the right arrow to get out of the square root symbol, then hit sine 32, and okay, there is the value for B, and then I'll do the same thing for A. I do square root 7, right, and then I've got to arrow out of the square root, and then say cosine 32, okay, and then there's that one, okay. So, let's see what we get here. So, square root 7 times the sine of 32 comes out to be about 1.40. And then over here, A square root 7 times the cosine of 32, 2.24. And then let's see, just for fun, if we do 1.4 squared plus 2.24 squared, do we get 7? Let's see, 1.4 squared and then 2.24 squared, 6.9776. So that's approximately equal to 7. We're off by 3/100ths or so, right? If we want better accuracy here, then we'd have to come back. These are exact, right? These values are exact right here, but as I like to say, exactly what? Because we don't really know what numbers those are, you know? So the approximation, we lose a little bit of accuracy, but at least we know what lengths we're working with. If we want better accuracy out of this, right, then we need some more digits up here, you know. I just kind of arbitrarily, we rounded to the hundredths place. You know, where you want to round off really depends on what you're doing, right? You know, if you're building something, you know, 1/100th of an inch is just a bunch of sawdust. It's not going to make that big a deal. But a lot of these machine tool parts and industrial manufacturing, you know, they go, you know, their accuracy has to be very, like 1/100th of an inch actually is a very big deal. Okay. All right. So that's it for section 1.3. We'll move on into the next section, start looking at these word problems. As always, if you have any questions about this, please let me know. Thanks.